with a client of ours, and Brooke discovered we were in town, so he immediately arranged for a meeting of the New York SIG APL. And about 40 people turned out. And we had questions about how to do a competition of APL and stuff. So he just thought that Morten and I waffled way too much. So he, during that meeting, got 2 major sponsors, decided how to organize the competition, what to be in it, signed up some judges, and just took it from there and got the ball rolling. I admire that kind of people. It's brilliant. Fiveserve has donated a major part of the sponsoring. There's an anonymous, also rather large contribution. And then Brooke has sponsored the judges and paid their fees, and also the fee to Project Euler. So it's a community exercise, this one. And today we are ready to see the result. And first I'd give the word to Brian Becker, who was one of the judges. We'll talk a little bit about that process and to do the drawing of the consolation prizes.
Thank you, Gitte. It was a great honor to be one of the judges for the APL Programming Contest. In case you don't know, Bob Pullman, who was here earlier today, was one of the other judges. And unfortunately, or fortunately, Bob's driving up to, I guess, Poughkeepsie now to visit some friends, so he wasn't able to stay on for the presentation today. But in case you don't know what the programming contest was about, the first 20 problems from the projecteuler.net website were selected, and the idea was that each of the contestants would solve as many of those problems as they could, and then turn in their submissions. A valid submission consisted of at least 3 problems, and submissions that were considered for the top 3 prizes, you had to solve all 20 correctly. And it was really pretty amazing. We had, I believe, 31 entries, and there was a variety of entries. Some people got all the problems right. Actually, most people got all the problems right. Ronald Chan's entry, he's our winner, was pretty amazing and actually quite humbling. I thought I knew APL and wrote reasonably decent code, and then comparing my solution to his, it was a more than humbling experience. But his solution actually ran about 40% faster than the next closest solution. And our second place, and Ronald also comes from New Zealand, so if we could have picked the farthest point possible to ship somebody to this conference, we somehow managed to do that. And Chris King was the second, or the runner-up, and his entry was sort of diametrically opposed from Ronald's in that Ronald clearly understood the mathematics behind most of the problems and just put an incredible amount of work into it. Or at least I hope it was an incredible amount of work, because if it wasn't, I'm even more humbled. And Chris King's entry, while it didn't run as fast, really demonstrated APL as a tool of notation of thought, because he used made extensive use of operators and a number of constructs that took me quite a while to figure out. So it was a lot of fun, and Bob and I judged all of the submissions independently, and our top 3 entrants wound up being the same set of people. So at least we correlated on that. Bob and I did have the pleasure of working together back around 1982, and so in 27 years somehow we've managed to stay in sync. So in any event, the other thing is there are consolation prizes that we're basically going to send out to people for having participated. And we were going to draw names out of a fishbowl or something like that, but since this is an APL conference, we decided we'd do something distinctly APL. So I've written a namespace here that has APL contest.run. It initializes quad RL to some value, and then goes and selects the hello. And then goes and selects the names. So without further ado, hopefully it works. Now it's saving an Excel worksheet behind. Well, this application went through a couple of iterations. Last night, I discovered that one person's name came up twice, and so I was dreadfully afraid, and I ran running over to Roger and Morton saying the roll function is broken in APL, because clearly I couldn't have made a mistake. Well, somebody had submitted a couple of iterations of workspaces, so his name snuck into the list twice. Well, that's been resolved. And then Vibeke asked me, she said, well, what are we going to do with the names? How are we going to save them? So version 2 of this goes out and saves an Excel spreadsheet in the background. So those are our 20 consolation prizes. And again, it's been a great honor to participate in this. And I guess it's going to run again next year. And if I'm lucky enough, I hope to participate then as well. Thank you.
Thank you, Brian. You'll enjoy the variety of names you saw there, because these submissions came from all over the world, and that's really great to see. Okay, and thank you for also announcing the winner. We were supposed to be Walt who did that. But a representative for the biggest sponsor for this competition, Walt Cisnenko from Fiserv.
Thank you very much. First of all, I'd like to say what a privilege it is for Fiserv Investment Services Organization to be a sponsor for the Worldwide APL Programming Contest. APL is a key element of our technology and business strategy, and it is critical for us to encourage and support the next generation of APL developers. I am very honored to be able to present to you Ronald, I know his name, the certificate and prize for first place in the APL Programming Contest. I wish you the best in your future endeavors and sincerely hope that this experience has encouraged you to continue your work with APL. Congratulations.
Okay, and so we have asked Ronald to speak a little bit about how he experienced his first endeavor with APL and how he managed to solve the problem such that he became the winner of the competition. And this young man is not only clever writing APL, he's also game, so he promised to come here and tell us about it. So, Ronald, are you online?
I don't necessarily need the internet.
No, I mean, are you up and running? So, go ahead.
Thank you. It was fun entering this competition, and so what I'm going to do is I'm going to show you how I did some of the programs, solve some of the solutions, and at the same time I'm going to talk about what I was thinking and sort of the process of solving it and things I've learnt as I've done it. So first of all, I've been to the International Olympiads for mathematics and also informatics. So those have really coloured the way I've solved these problems. Now, I found out about this contest from a lecturer at my university who emailed me. So I had a look at the Project Euler site. I thought, maybe I should do this competition. Once I looked at the questions, I thought, these are really easy. And they are, in fact, a lot easier than problems I've done before. But I also thought, if I think it's easy, lots of people are going to think it's easy. And I think before, how many people actually got 20 out of 20?
I think it was about 18, 19.
Yep. So I thought, okay, lots of people are going to get 20 out of 20. And I was thinking, how do I win? Because I want to win, of course. So I decided that I needed to really optimize my code and work out how to solve them the best way I can. So I'm going to start with showing you what my solutions were. And I'm going to do it in the order that I solved them in, mostly. So how do you increase? Right there. Okay, so question 1 was the first question I did. Okay, so are there people who haven't got the questions, by the way? Yes, okay. These are the questions which I opened before I took my laptop down here, so even though there's no internet connection, I can see all the questions. And I hope that okay, so the first problem, add all the natural numbers below 1,000 that are multiples of 3 or 5. That's really easy. In fact, actually, all of them are easy to just be able to give the answer to. But the easiest way is not necessarily the best way. Of course, since there's only 1,000, you could easily do it. I mean, make all 1,000 integers, check all that are multiples of 3, check all that are multiples of 5, union them and add them all together. But of course, that's not necessarily the fastest way. So, actually, first I'll split this up into some easier subproblem. So, can I write directly on here? Yeah. Okay. So, here's a formal sort of thing about properties. So, I'm going to say that union of P1, P2, Okay, so here I've actually put property 1, property 2, and so on. So you say you have n properties, and you want to get a union of them. That's just the property of each of them added together, and then you add the intersection of pairs of properties, every combination, then combinations of 3 multiplied together, and so on until you have all of them multiplied together. Now that's a really formal sort of thing where, oh, sorry, I've made a mistake. You subtract the next line, you add the next line, then you subtract the next line. And so this is actually plus or minus, which depends whether it's an odd or even line. Okay, so that's the formal thing, but in this case, actually, it's really simple because you just have to add all the ones which are multiples of 3, then add all the ones which are multiples of 5, then subtract all the ones which are multiples of both of them. So that's what I did at first. That was my first submission. I've actually also made another quick formula, just in case anyone doesn't know it. This is summing order numbers 1 to n. And to make it work, all I had to do was make this function, which is sum 1 to y, and this function, which sums or the multiples of x up to y. So that's basically saying that n is equal to y by x, and then that's the number of integers you want to sum, and x is the multiple of the numbers you want to sum. But just for a little fun, I decided, okay, so because I have this function here, you could just say that the answer is 3 sum of multiples to 999 plus 5 sum of multiples to 999 minus 15 sum of multiples 999. But I decided, and this was, I think, one of my last submissions, to make it so that y can be itself an array. So all I'd have to do x can be an array. So all I'd have to do is 3 space 5 sum of multiples to 999. So this is what I've done. Right, yes, these 2 lines. Can you see how it works? Okay, I wrote it like this because it would be faster than if I didn't write it like this. I could actually have done a loop through all the lines and then perhaps done a loop through each of these terms. But in this case, you can see that there are no loops. All I've done is let's see, I know the idea, but I can't. Perhaps I'd have to read all the comments, but they're all here. All I did was, these actually contain every subset of this. Because just pick some of these properties and just choose them, and you'll find the term somewhere here. So that's what that does. It gets a binary array of all possible combinations. And it actually gives a matrix. So in the rows, it has all the combinations, and in the columns, it has the zeros and ones. And then I just multiply it with the property. And then after I do that, I work out the sign, which is not hard because you just count how many properties there are. If there's 1, then you have it plus. If there's if it's an odd number, you want to add it, and if it's an even number, you want to subtract it. So that's question 1. The next one I did was question 2, which is finding the Fibonacci numbers. So all I did was I wrapped it in a function, sum of even Fibonacci. And, right, of course. Okay. Again, you could have added the sum of all the even Fibonacci numbers, but I decided there must be a simpler way of doing that. On Wikipedia, there's a formula for summing every second Fibonacci number. But in this case, we want to sum every third Fibonacci number. So if you look at the comments, after all this derivation, you will get this as being the same as the original thing you wanted to do, which was this. And this actually took me hours. I was looking at the Wikipedia derivation for summing every second Fibonacci number and trying to work out how to fit that into every third one. But eventually I came up with this, which is just sum of this Fibonacci number plus this Fibonacci number minus this Fibonacci number. So that was good. And then to implement the Fibonacci thing, I just used the Fibonacci formula Now, this is actually not very important because even if you try to calculate all the smaller Fibonacci numbers, it's not going to be much slower because the Fibonacci sequence actually increases exponentially. So it's very fast. You'll run out of precision before you run out of time, no matter how quickly you want to do it. And it's less than 1 millisecond. The next one I did was 5. Right, this was really, really easy just because it's APL. Everyone will understand this. So I'm not going to say much more on this. 16. Right. Actually, there's a whole class of problems which are similar to this one. And they include okay. What is the sum of the digits of the number 2 to the power of 1,000? So if you just get 2 to the power of 1,000, just add all the digits up and that will be the answer. But look at this question. Find the sum of digits in 100 factorial. They're actually very similar because the operations, well, the calculation is not hard. The main thing is that there's an arbitrary number of decimal digits. So my solution, the solution that I came up with was a class digit array. Actually, in DFNS, there's a big operator, is it? Or yeah, that will do the same thing, but I decided not to use it. In all languages, string manipulation tends to be slow. So it was a lot of code and I didn't bother looking that much into it, but I suspect it's slower. Digit array actually doesn't have the actual arrays. It actually is a collection of functions which operates on arrays. So I've got a set base, which was actually useful. And then I've got some functions which multiply, add, subtract. I did this divide thing. I never actually used it. It was for fun. And actually it's slow. In software, adding and subtracting is fast. Multiplication tends to be slower and division is the slowest of all. And the code is horrible. But nevertheless, since I didn't use it, it doesn't really matter that much. I had some functions to do some utility functions. They just make x and y the same size in some cases, removes leading zeros. Oh, right. How does digit array work? Well, it's just an array of digits, and for example, I had the number 3, 8. If I had this array, then the number it represents is just 389, if the base is 10. So I did all that, and then I could just plug it straight into my solution. That was 16. But do you notice that I've done a bit more coding than I needed to? See, all I had to do is say, if I just make a new instance of digit array here, I mean, I could have just gone da.multiply / And then, so it's this one, 100/2. And that would do it all. Is that correct? It looks. All right, 1,000, sorry. It's taking a while. My solution took 51 milliseconds, and that's what all the other code does. Set base, 10 million. Anyone know why I want to do that? Who said yes? Okay, can someone tell me why?
Try to keep your interest low through the first question.
Yes. But why does it just speed it up so much? Yeah. So, see, in hardware you can add up or multiply integers no matter what their size, as long as they're less than 32 bits. So it's a waste to try and multiply 4 and 5 and numbers less than 10. So that's what this does. Then here I'm doing it a bunch at a time. So I've got 2 to the 25, which fits in 32 bits. And I'm just doing 40 of them. So 40 times 25, that's 1,000. And then some processing and output it. And that's exactly the same thing in this one. I can't actually see where I set the base, but I think I did. I must have. Because it's only taking 54 seconds. Okay, so that's that class of things. Then there was a second class of problems that were similar. And they were similar because they all were about primes. So again, I made a class called primes. I've actually got a variable to keep track of all the primes I've found so far. And for this question, I don't think it actually helps much. But you'll see soon why I have this. And it just keeps track of what number I've found the prime to. And the algorithm I used is the sieve of Eratosthenes. Do people know how it works, or? Oh, sorry. I've forgotten to give you the problem. Yes, calculate the sum of all primes below 2 million. But then the other prime, yep, 3 is similar, 7, and you won't think it's similar, or quite similar, but it's kind of similar, which is the one which says it's the one about triangular numbers. No, that's the triangle. It is to find the first triangular, the first triangular number with over 500 divisors. I didn't actually use the same code, but the code that is written is similar. But I used the sieve of Eratosthenes, which is, in high school you would have learnt this 10 by 10 sort of table with all the integers 1 to 100, and then you'd get the first prime, which is 2, and you'd cross off all the multiples. Then you get the next prime, 3, cross off all the multiples, and then 5, and then 7, and cross off all their multiples, and then the ones left are primes. So same principle. But this is actually what I did. Sieve 2. I split it into 2 parts, which is to sieve all the primes that I've already found, and then sieve all the primes that I've found just now. That is in this function. Right, the crossing off. To cross it off, I've just crossed off a whole arithmetic progression. But what's important is that I start crossing off at p squared. Because every multiple which is less than p squared, but still a multiple, is also a multiple of a prime which is smaller. So say 5p is less than p squared. Then it have been crossed off when I cross off all the multiples of 5. And that's actually a very, very important limit, because by doing that, if say I have a prime which is 101, and p squared starts at 10,000, and I want to find all the primes up to 11,000, then I've basically just said I don't need to cross off anything in this whole section, and I only need to cross off the ones in this small section. So that's a real big optimization. The second thing is that the difference between the is 2 times the prime. Because if it's 4p, well, that's already crossed off by 2, and if it's 10p, it's already crossed off by 2. So the only p's I want to multiples of p that I want to cross off are the odd ones. So that's another thing. So that's that part. And I just extract it, so nothing difficult. Right. There is actually some overhead when I use the sift2 function more than once. So say I want to find all the primes up to 1,000. If instead I said sift to 500 and then sift to 1,000, there's actually some overhead to do with that, but it should be constant. No, it's not constant overhead. There is some overhead, but it's small. But the ability to do that actually is quite important. But for now, that's not necessary for this one, which is just to sum the prime list of 2 million. Prime list is another function which is the same as sift2 in a way, except it returns the prime up to a certain number, and if it hasn't sifted to that point, it automatically calls sift2. That's question 10, and naturally, question 7 is the one which is most similar. So find a 10,001st prime. This is... okay, right. In this case, what I did was I found the largest number the nth prime can be. And on Wikipedia, there will be a formula for the upper bound. And it's here. And so then I just sift to that upper bound, then I'll know that I have the prime already. So that goes in there, and then I just output it. So that's really simple. And of course, I don't want to call the sift2 function many times until I get the prime, because there's overhead. But wait, that's not right. 3. Right. This one, decompose. Okay, so decompose. To find the prime factors of a number, you use trial division. You don't use trial division if you want all the primes up to a certain number, because that's slower. But in this case, I just have one single number, so you use trial division. And what I've done here is I've grouped them together. So what I'd do in a normal programming language, or like C or C++, is I'd say divide by 2, divide by 3, divide by 5, and so on and so on. But instead, actually, what I've done is I've said divide it by order primes less than 10. Divide the number by order primes less than 100, and so on, just to cut down on the number of loops. So this doesn't actually loop that many times. And there's just a whole bunch of equations just to make it so that I can do that loop, and to keep track of all the factors I have. This is quite a bit of code, so it will probably take a bit of time to understand everything. But that's essentially what it does. Next question. Okay, right. Question 4 was the next one I did, but it was actually one of the last that I updated. My first solution for question 9 was, question 4, sorry, which is to find the largest palindrome, which is the product of two 3-digit numbers. The first one I did was kind of brute force. You just basically check everything and you'll get it. The next one I did was that I only did it for the numbers 900 to 1000 because I know that this pattern guarantees it. Because 902 times 909 is a palindrome, but then you can add an arbitrary number of zeros and you still have a palindrome. But actually the answer is much bigger than that. So that wasn't very fast. And the other optimization I found was that for 3-digit numbers, for 5-digit palindromes, or in fact any odd-digit palindrome, it's divisible by 11. So that was another optimization I did. But at the end I decided, no, I'll rewrite all the code. So in fact, before what I had was, this solution would give you the answer to, if you had 2 n-digit numbers, but now it says n is the I think it is n, but you can basically find the largest palindrome, which is made up of 2 numbers, which is less than any number, not just at the digit boundaries. To do that, actually, it's kind of still brute force, but it's a better brute force. In this case, you have your search space, which is a square, and you want to find the ones which is closer to here. This is the largest number you can get, but it's not necessarily a palindrome. And these contours show how they reduce in size. So what I did was I calculated this contour first, then I did a brute force on everything here. Checked if there was a palindrome. If there was, find the largest, and then that's your answer. If not, calculate another contour, then another, and so on until you have your answer. Actually, calculating the contours is overhead, and you don't want overhead. At least you want to limit it. So what I actually do is, first, I make this contour very small. Then I might make the next contour twice the area, and twice the area again and again and again. And that's actually a very good guarantee. Who knows what I'm talking about when I talk about algorithmic complexity? Okay. Now, when you think of algorithms, you have this so-called big O notation. So, if I say an algorithm takes O(n) time, then it means it takes linear time. If n was twice as big, it'd take twice the time. But then you can get things like O(n) squared time and so on. Now, assuming you knew the answer and you were trying to find the answer, assuming you knew the answer and you wanted to check that it was the correct answer, you could calculate the contour which intersects your current answer, and then check this area. So your algorithm for brute force checking of it is just O times the O of the area there. But of course you don't know it. So how do you do it without increasing this? Right, one more thing is that the big O notation takes out the constant. So if it takes 2n time, then we ignore the 2. If it takes 5n squared plus 3n time, then we just take n squared, which is the largest term. But by doubling the area, it means that the most work I'll have to do is 2 times the area, which is still O of area. So that's why I've done that. I can't remember if I've actually used 2. I might have used some other. Right, 1.5 times the area each iteration. And the other thing is that by multiplying by 2 or 1.5, I know that the maximum overhead is log n time. Because if I have 1,000,000 and I used 2 instead of 1.5, then I'd only have to go through it at most 10 times. That's the loop. Because every time I go through a loop, it's a lot of overhead. APL is interpreted, and when you have interpreted languages, you don't want to loop that many times. So that was that question.
What was the answer?
Here. That's the answer. Question 13, I actually used digit array again. You were actually given the 50-digit numbers, and so I just read it in, put it through digit array because that's arbitrarily long, and then that's basically the answer. So very simple after I wrote that class. Next one I did was 18. Who knows what dynamic programming is? Okay, that is the answer. And that is the answer that is probably the fastest you can get. Basically, what they had was they had a number of, well, many numbers in a triangle, and you wanted to find a path from here to the bottom of the triangle somewhere. Now there's many possible paths. And you want to find a minimum sum, right? Yes, the minimum sum. Maximum. Maximum sum, okay. Doesn't really matter, it's the same algorithm. Dynamic programming involves just finding the subproblem, so what's the fastest way of getting to here? Oh, sorry, not fastest, I'm thinking of Dijkstra. What's the maximum sum I can get if I go from the bottom to here? Okay. The answer is the answer to this plus 3, or the answer to this plus 3. Can you see that it's a very simple check? And then you just do that starting from the bottom of the triangle until you get to the top. And then there's your answer. It just magically pops out. and it only takes, well, the time it takes is only the number of numbers that you have instead of an exponential check all paths possible brute force kind of approach. So that's what this does. And the comments tell you how it works. So that's question 8. The next one is 18. Wait, no, that was question 18. Ah, that's what this does. Then what was question 8? Oh, right, question 8. So basically what they had was they had a 1,000 digit number and you wanted to find the largest product of 5 consecutive digits. So that was just, well, there wasn't an easy way to go about it. You just had to do it the way it's stated, which is just to do some indexing work, then multiply each group of 5, and find the largest. So there wasn't an easy way to do it. Wait, why did I use digit? Ah, right. I used digit array because I made a function called digitize a string, which is just to make a string into digits, and digit array actually splits the string into separate digits as an array, so that was nice to work with, and that's why I used it. So no easy way, just do it how it says to do it. Ah, 9 was quite interesting. It is finding the only Pythagorean triplet, ABC, where A plus B plus C is equal to 1,000. So a Pythagorean triplet is where A squared plus B squared equals C squared. You can do it in a brute force way, and that's going to be fast enough. But what I did instead was I did some number theory work from what I knew when I did the Mathematical Olympiad. So first you find these weird formulas for A, B, and C, and then you just do some stuff. The derivation's all here. And then you find that this is true. So K times M times N plus M is equal to N, which is 1,000, because that's coming from here, divided by 2. And that's actually very good, because that means that K is a factor, M is a factor, and N plus M is also a factor. And N, 500, has a limited number of factors. So my solution can work with N being 1,000,000 or something like that, because this really cuts down on the search space. So this is the algorithm in comments, and then it just goes through, finds all the factors, and then tries to fit all the factors in K, M, and N. And that's pretty much all it does. The loop is to check each combination of factors that you can have. So, yeah, that's pretty much all it was. 15. Right. So starting in the top left corner of a 20 by 20 grid, of a 3 by 3 grid, how many routes are there from here to here? And you can only go right or down. This looks actually a lot like dynamic programming. And in fact, that is what you would use if you had a grid. If you had a grid with holes in it, dynamic programming is in fact what you would do. But in this case, you can actually list these as instructions. So you can say RD, RD, and that's this route. And any permutation of 2 R's and 2 D's would be an answer. So actually it's just 40C20, and I made it NCM, where N and M were the dimensions. I made my own combination function, and that actually is quite interesting because, okay, 40 factorial 20, wait, no, it's the other way around. Okay, that's all right, but do you notice something strange about it? Whoops. All right, that's, I think that the Dyalog one is suffering from precision problems. This is, oh wait, no, that's not right. Yes. All right, and my function doesn't have the decimal point, which is correct. Now, if I remember correctly, I've done something to make it so it doesn't do that. I think I found the LCM of two numbers and then used that instead. Because how do you find this? Say you didn't have the factorial function. You could go 50, then you'd go 50 times 49 divided by 2, and that would give you the next answer, and then you'd go 1225 times 48 divided by 3. Wait, no, that's not correct. Oh, right, no wonder. Well, anyways, that's how it works. But the problem is, you want to do the division first for some reason, which is that if you do the multiplication, it can get too big, but if you did the division first, then it won't get too big. Unfortunately, the division suffers from problems with a floating point, because sometimes you can't represent it exactly. So I think what I did was I found the LCM, no. I found a GCD of, say, 48 and 3, and then divided both by the GCD, and then used that instead. So then you won't have a chance of getting a fraction at any point. Yes. Okay. Then I'll do the last problem which I did, because that's one I really want to show you. This is the one that I had most trouble with. Now, in any other language, okay, 14 is find the longest sequence using a starting number under 1 million, and the sequence is n by 2 is the next number in the sequence if it's n is even, otherwise it's 3n plus 1. It actually hasn't been proven that every starting number gets to 1. So there's a chance that my program will not finish running if you use a suitable starting number. But maybe it will if the collapse thing is proved correct. So that's actually the sequence name on that database of sequences. Okay, so to do that, what's most important is my simultaneous simulation process. Because what you basically have is you have a tree, and so you have 4, and well, basically you have a tree which goes on and goes on forever. But, alright, but you don't want to start at every possible number and then do it until you get to 1, because that's slow. That's a lot of loops, it's slow. So what you do is you find everything, you get every integer less than 1 million. Then you perform that. Then, for those which are less than 1 million, you know that the answer is, you know what the answer is in a way. If this goes to this, then you know that the answer to this is 1 plus this, because the question is, what is the sequence? How long is the sequence? So the sequence is 1 more than that. But if it's greater than 1 million, you have to keep doing it until you get less than 1 million. And you do that again and again until until you have nothing left. And then you go through half founds, which is possibly things like this, which goes from here to here, and then you say, okay, that's enough. I've finished, found the answer. Actually, you've half found it in a way. And since you've half found it, at the end, you have to go back and say, what's my answer for 2? And then do it. And that's basically all I've done. Oh, and that's enough to give you the answer. So you just then find the maximum of the sequence length. But then I wrote this explode from. This actually makes it go much, much faster. Without this, it's 8 seconds. With this, it's 3 seconds. This actually goes from the top and says, okay, this is a sequence length of 1, and then it goes to its children, or goes down here and say, okay, it's a sequence of 2, and then keeps going and going, and then just filling it all in. And that's really fast because you can do each layer one at a time in each loop, and then at some point the layer gets so big that you're just doing this whole big chunk of it all at the same time, and it's really fast. There's one problem though. If it then gets above 1 million, should I throw it away or should I keep it for now? Doesn't know, so it just cuts it off when it gets above 1 million. And then, of course, that leaves many holes, and that's what my simultaneous simulation function does. Fills in all the holes, and then that's it. And the reason I had so much problems with this one was that my first one was not a parallel sort of simulation. It was just finding each one individually. And it took a minute to run, whereas this one only takes 3 seconds. I can do the benchmark again of everything. In fact, it's not 3 seconds, this time it is. That's just a glitch, I assure you. Or maybe okay, the first one I know. That's the usual one that I get. So the whole thing actually, all my solutions run in less than 3 seconds. And I think that's all I have time for.